For centuries, we've been trying to crack the code of the human brain. And just when we think we're finally getting somewhere, it throws a new mystery at us, something that challenges everything we thought we knew. We're going to dive into some of these hidden signals, this secret language our brain is speaking, a language we're really only just starting to translate. We've all heard the analogy a million times, right? The brain is like a computer, and a computer's most basic part, a transistor, is super simple. It's either on or it's off, 1 or 0. For the longest time, we kind of thought neurons were the same deal. Either they fire or they don't. But as you can see here, yeah, that simple comparison is totally falling apart. The human neuron, it's a much, much bigger question mark. So let's dive right into that mystery, because it turns out the very building blocks of our thoughts, the neurons themselves, have this hidden language that goes way, way beyond a simple on or off switch. Okay, so check this out. In 2020, researchers found something brand new, something hiding in our cortical cells all this time. They figured out that our neurons don't just use sodium to fire off a signal. They also use calcium, and this creates a totally different type of signal, what they call a dCAAP. Now, this isn't just on or off. It's a graded signal. Think of it like having a dimmer switch instead of a regular light switch. It's got nuance. And you can just feel the excitement from the scientists themselves. One of them, Matthew Larkham, said there was a genuine eureka moment when they saw these signals for the first time. I mean, can you imagine? Discovering a new form of communication inside the brain is like finding a whole new letter in the alphabet. It changes how you read everything. So what does this new dimmer switch actually do? Well, it completely changes the brain's computing power. We used to think a single neuron could only do simple logic, like and or. But with these new graded signals, just one neuron can now perform a much more complex function called an exclusive or XOR. That means choosing one thing or another, but not both. That's a level of computation that scientists used to think required an entire network of neurons to pull off. And the complexity doesn't stop there. Even the connections between the neurons, the synapses, aren't what we thought. We used to picture a simple two-way conversation, but it turns out it's more like a three-way conference call. There's this third cell, a type of glial cell called an astrocyte, that is an active participant. It's listening in, and it's even influencing the conversation. Now, this isn't all just abstract science. Decoding these hidden signals has some profound real-world consequences for our health. It can even help predict what's coming down the road for us. And believe me, the stakes are incredibly high. For patients in a coma, a tiny, almost hidden signal called a sleep spindle, it's this little burst of brain activity during sleep, is a massive predictor of recovery. Just look at the chart. Patients who have these spindles have a dramatically better chance of functional recovery. That little signal, it's a true signal of hope. But this example might be even more stunning. Researchers have found a protein signal called TSPO. It's linked to brain inflammation, and it can start to rise in people at high risk for Alzheimer's when they're in their early 20s. That's a full 2 decades before the first symptoms, like memory loss, even show up. It's like a hidden warning flare firing deep inside the brain long before the storm arrives. Okay, so let's zoom out for a second. We've been looking at these tiny signals, but what about the brain's overall management? It's like there's this hidden operating system running in the background with all these invisible processes that guide how you think and focus every single moment of the day. I mean, really think about it. With all the chaos and distractions in the world, your phone buzzing, emails popping up, how does your brain actually manage to stay on task? Well, the answer is just incredible. When you get distracted, your brain doesn't just, try harder. Instead, neurons in your prefrontal cortex start firing in this coordinated, rotating wave. These waves literally herd your thoughts back to where they're supposed to be. If the wave makes a full circle, you're back on track. If it falls short, you make a mistake. It's that direct. And what about making a decision? When you're facing a bunch of different options, how does your brain actually cut through all that noise to make a choice? It's not chaos in there. It's actually a pretty organized process. According to this latent circuit model, your brain appoints a little group of ringleader neurons, and their job is to take charge and actively silence all the chatter from other circuits that are processing irrelevant stuff. By just quieting down all that noise, they clear a path so you can make one focused decision. So, with this staggering level of complexity, all these signals and systems, how could we ever hope to see the full picture?
Well, to even try, scientists recently undertook this monumental project to create the most detailed blueprint of the brain ever attempted, to do what was once thought to be impossible.
The scale of this project, it's just mind-boggling. They mapped a tiny piece of mouse brain tissue, no bigger than a grain of sand. The data they generated from that one little speck, 1.6 petabytes. To put that in perspective for you, that's the same as watching 22 straight years of nonstop high-definition video. And inside that single grain of sand, they reconstructed and mapped over 500 million individual connections between neurons. Just let that sink in. One researcher called it an exquisite forest of architecture, and that feels about right. And here's the real kicker. This achievement is even crazier when you realize that back in 1979, Francis Crick, one of the guys who co-discovered the structure of DNA, he said that doing this exact thing would be impossible. And yet, here we are. But just as we're celebrating this incredible map, a new discovery comes along. It's humbling. It turns out that even our most advanced tools are missing a huge piece of the puzzle. There's a veritable ghost in the machine. Okay, so let's start with our best tool for watching a living, working brain, the fMRI. It's what gives us those beautiful, colorful images of brain activity. And the way it works is by tracking changes in blood flow. The basic assumption has always been more blood flow means more brain activity. Simple enough, right? Well, here's the paradox. When scientists measured blood flow with fMRI and recorded the electrical zaps from neurons directly at the same time, they found this really strange mismatch. The maps of which areas were active, they lined up perfectly. But when they looked at the timing of the signals, they were completely out of sync, not even close. The only logical conclusion is that the blood flow the fMRI is seeing is being driven by something else, something our electrical sensors can't even pick up. There is an entire layer of brain activity that has been completely invisible to us this whole time, what scientists are now calling electrophysiology invisible signals. So our journey into the brain's hidden signals has led us to this amazing and kind of bewildering place. We've gone from thinking about simple on-off switches to complex logic, from two-way chats to three-way conference calls, and from mapping the impossible to discovering signals that are literally invisible. It seems like every answer we find just reveals a deeper, more profound mystery. It really makes you wonder, what other secrets is the brain still hiding?